go live.
Okay.
Yeah?
No, okay, it was for the live.
Okay, we're ready to start. Let's go. So, hello everyone. I'm Maura Pintor and I'm a postdoctoral researcher at University of Cagliari. Welcome to a new event of our machine learning security seminar series. Today we have Fabio Brau as a guest. But right before we start, I would like to share with you some info. So the event today is live streamed and recorded. So if you don't want to be recorded, feel free to follow on YouTube. But if you do, just take care that we will prioritize the questions from the Zoom call. So raise hand first or comments, and then we will look at the chat on YouTube, but later, and if there is some time left. Then if you want to know more about the seminars and be always updated on the new seminars we plan and we schedule, follow us on Twitter, LinkedIn, or Eventbrite, or any other link. Luca will share them in the chat, both on Zoom and YouTube. And finally, if you want to know more about machine learning security, or maybe you need more basic topics, feel free to check out the same YouTube channel where we are live streaming, where we have a free course on machine learning security available to everyone. I'd like to thank, as always, the people who helped me organize these seminars. So thank you all, guys. And now I leave the stage to Luca, who will introduce the speaker for today.
Thank you. So hello, everybody. So our host today is Fabio Brau, and he's a PhD student at the Department of Excellence in Robotics and AI at the Scuola Superiore Sant'Anna in Pisa. And he works in the RETIS laboratory. He obtained his master's degree in mathematics from the University of Pisa, where he specialized in numerical analysis. And currently he is studying the robustness of deep neural networks against adversarial examples. And both from a practical and a theoretical perspective, leveraging some geometrical results and the properties of classification models' decision boundaries. So thank you again for being here. The stage is all yours.
Hi, everyone. I share my screen. Can you see my screen?
Yes, we can.
Yes.
Okay. So thanks a lot for inviting me to this series of seminars. And yes, this presentation is related to the online certifiable robustness for adversarial perturbation. I will start the presentation by introducing the problem of robust classification and the existence of adversarial examples in deep neural networks. Then I will present you the problem of online minimal adversarial perturbation and how it can be computed. And finally, I will introduce the sign distance classifier, that is a classification model that we recently presented in a work. First of all, I want to give you a geometrical intuition behind classifiers. Basically, when we have to deal with images or sounds, we are under the hypothesis of continuous input domain, or at least the input domain can be approximately said continuous. In this case, a classifier needs to divide the input domain into regions so that two samples of the same regions are classified in the same manner. Now, between two regions, there are tiny portions of the space that are called decision boundary or classification boundary, in which the class changes from one to another. Those regions are particularly interesting since they represent the edge of the regions, of the classification regions, and the classifiers typically feature undefined behavior. And this is maybe one of the reasons of the existence adversarial examples. In fact, adversarial examples recently grew popularity in the literature. It can be studied by many different points of view, but at least two of them are really important. From the point of view of the security, they represent for sure a security threat. In fact, they can be maliciously computed and printed or also recorded from an attacker. They can be perceived directly from cameras or microphones without that the attacker needs to inject them directly inside of the model. And of course, they can cause a failure of the safety critical system. For example, a segmentation model in a self-driving vehicle can be fooled by an adversarial patch that can be that lay on the street, on the road. The adversarial patch can cause a misclassification of the pixel and hence a failure of the critical system. From a modelistic point of view, adversarial example represent also a proof of lack of robustness. They in fact suggest that decision boundaries are really close in some sense to training and testing samples. This idea comes out from the fact that we know that by adding noise to an image, for example, random noise, the amount of noise that we need in order to fool the model is pretty huge. For example, we can see here that a sigma of 0.5, where sigma is the standard deviation, is required in order to fool a ResNet that classifies images of ImageNet. On the other side, adversarial perturbations can be computed. They are particularly small, and this is really the problem, the issue of the topic. That is, adversarial examples are close to decision boundaries, and then this property is an intrinsic property of the model that in some sense lacks in robustness. In this table here, we can see the average magnitude of the minimal adversarial perturbation, or the smallest adversarial perturbation that we need to add to images for a few standard data sets in order to fool the model. We can see that the values respect to the noise on the Gaussian noise is really small. In fact, the Gaussian noise would feature a magnitude of 0.5 if the standard deviation is 0.5. Hence, this is the reason why this presentation focuses on the robustness of deep neural networks under digital adversarial examples. Digital adversarial examples are perturbations that can be added to each pixel of the image, and we study the magnitude of the adversarial perturbation under the Euclidean norm. So before introducing the robustness, clearly an interesting topic is the minimal adversarial problem, or how to find the minimal adversarial perturbation. We know that from a geometrical point of view, a sample can be just like this point in blue, can be perturbed by adding some noise in order to cross the decision boundary, so that the point can reach the adversarial region. Of course, there are many perturbations that we can add in order to shift this point into the other region. However, there is one, a particular one, that is the smallest perturbation. The smallest perturbation can be computed by solving this minimum problem. That is basically the problem of the distance of a point from a set B, and this problem can be particularly tough. The minimal adversarial perturbation is interesting because it provides a certification of the robustness of the classification. Remember that a classification in a point X is robust, or epsilon robust, if it does not change under perturbation of the input of magnitude lower than epsilon. We can see, for example, here that a blue point, like this one, cannot be perturbed with a perturbation of magnitude lower than epsilon in order to reach the other region. Hence, we can say that the classification in this point is epsilon robust. On the other side, we have that the black point here can be perturbed by a small perturbation. Small, it means lower than epsilon, so that it reaches the other region. This is the beginning of the studies. In particular, we can ask how to find the minimal adversarial perturbation. The problem of finding the minimal adversarial perturbation is known in the literature, as it is widely studied. Remember that it is important since the classification in this point can be certified to be D of X robust, where D is the minimal adversarial perturbation. The oldest methods we can say there are two of them, the most famous, but there are many others and in the literature. Usually they are pretty accurate. They provide guarantees of success, but they require a lot of inferences of the model. A lot of inference translate into a lot of time that we have to wait in order to have the computation. Other methods that are pretty famous, for example, deep full decoupling direction norm, they provide an approximated solution and without guarantees, in the sense that we cannot bound the error of the estimation, so how much the approximation is accurate. However, they perform such a computation in a rapid manner, around 20 iterations, around 20 forwards, or 1,000 of forwards. In this first work, we wanted to find an approximated solution, but that provides guarantees of success, and that bounds the error of the estimation, but with few inferences, so that this problem can be solved in an online fashion. The idea is that we aim at estimating the real distance t by considering an approximated distance t that can be so in the yellow line. If this inequality holds, that is, the distance t can be upper bounded by t, and t divided by a coefficient rho is a lower bound of d, then we can say that the classification is robust against perturbation of magnitude lower than the coefficient that we can see here, that is t divided by rho. So we switch to the problem of finding an estimation in the form of t. In the work, we proved that the estimation of t can be found pretty easily by considering a point x and considering the direction provided by the gradient in x. We can see, in fact, that by moving from x toward the direction provided by the gradient and searching for the minimal intersection, for the closest intersection within the boundary, then we have a good approximation of t. The goodness of the approximation is also stated by a theorem that it can be proved, so that due to continuous property of the input space, we can say that there exists a certification radius named sigma, so that the inequality holds in a neighborhood of the boundary B. The neighborhood is called tubular neighborhood, and basically is formed by all the points that has a distance lower than sigma with respect to decision boundary. We can see that the problem that we need to solve is a minimal root problem, that is the smallest root of this equation. However, this equation, of course, is not linear, hence this problem can be solved by, it's not easy to solve this problem, however, can be tackled by bisection methods or Newton-like methods. To prove empirically that the estimation holds in the neighborhood of the boundary, we use 4 datasets pretty common: MNIST, Fashion-MNIST, CIFAR-10, and German traffic sign. That is the dataset of the street sign recognition. In a first experiment, we want to highlight the accuracy of the estimation of the ground truth distance t within the estimated distance t. In this case, the ground truth distance can be obtained by solving a minimum problem by considering the minimum of many solutions given by different algorithms. The algorithms that we use are iterative penalty, deep full, and decoupling direction norm, where iterative penalty is similar to Carlini-Wagner method, and all of them it requires a lot of forwards of the model. The estimated distance can be computed with various methods, for example, bisection and Newton method 1. On the figure, we can see that each point represents a sample of the dataset. On the x-axis, we have the ground truth, and on the y-axis, the estimated distance, and the straight lines represent the validity of the inequality. In particular, we can see that almost all the points are above the green line, and hence the inequality in green holds. In particular, the estimated distance t is always greater than the ground truth distance, the real distance. The other lines show that the other inequality holds. This is the left-hand inequality, and it is the most important since it allows to provide certifiable guarantees of the robustness. And we can see that close to the decision boundary, so that when the points are close to the zero, to the origin, we have that many of them are below the lines. Of course, the slope of the line depends on the parameter, on the coefficient rho, and so the coefficient rho decide how much the estimation is accurate. On another experiment, we estimate the certification radius of the theorem, that is the radius for which theoretically the inequality holds, and we use this estimation to provide a verification strategy. In particular, we can see here that above the certification line, the red line, there are attacks of magnitude lower than t divided by rho, but below this line, there are no attacks. This can be translated to saying that below the line, we can detect and we can certify that the classification cannot be fooled by an attack with this magnitude. This is one of the most important experiments of the work. And finally, just to summarize, we shown that the method that we proposed is able to provide a computation of the minimal adversarial perturbation. The computation is approximated. However, the method provides guarantees on the bound of the error. Most importantly, the number of inferences that we need to evaluate this distance is bounded at around 220. Hence, this method can be applied online. In particular, the applications are online robustness certification, online verification if we are below sigma, and we have to prove that we are below sigma, or also fast adversarial example generation. This is the end of a first method that provides certifiable robustness. Another interesting argument or topic is given by the sign distance classifier. First of all, I want to give you an idea of the motivation behind this classifier. In particular, we were searching for a function f for which the methods that we developed before, it provides or are able to provide an exact solution. So we want to act on the function, on the classifier, rather than on the method that computes distance. We aim at finding this function so that the approximated method is still with guarantees, and we aim at finding a function f so that the number of inferences are just one. So the only solution is that the output of the function must provide directly the minimal adversarial perturbation. So that we search, in other words, we search for a function that it provides guarantees by construction. In the literature, there are already classifiers that provide certifiable robust classification by construction. Just to mention two of them, they are Lipschitz-bounded neural networks and the classification by randomized smoothing. Remember that a Lipschitz-bounded neural network is a function so that the input, the perturbation of the input is a bound, it provides a bound on the perturbation of the output. It's easy to prove that for this kind of functions, we can find this radius R that only depends on the output of the function, so that the classification is R robust. This is the aim of many recent works. The classification via randomized smoothing instead are a different method that is not actually online, but in other terms, by considering this this formula here, it provides again a radius for which the classification is robust. The model that we proposed, that is a signed distance classifier, is an instance of bounded neural network, but with some property more. The signed distance classifier depends on the distance function of a point x from a boundary set B. That is the minimum distance of x from each point of the set B. When the set B is a frontier of another set, for example, the set E, then the signed distance function can be defined so that the module of the function is the same of the distance from x to B, and the sign is positive or negative, depending whether the point is inside or outside the set E. The first interesting property of the signed distance function is that they perform binary classification. In fact, remember that the classification obtained from a scalar valued function f can be obtained by considering only the sign of the function f. We are not interested in the value of the function. For this reason, if we consider the set E of all the points for which the function takes negative value, then the classification provided by the signed distance function and the classification provided by the function f are exactly the same. This is a good property since it allows to say that signed distance function can somehow substitute or can be substituted to the general function for binary classification. The second important property is basically the robustness by design of the function. In fact, we know that if we consider the radius r given by the module of the function, then each perturbation delta can be added to the point x, and we know by construction that the classification of x and the classification of the perturbed input would be the same. In the figure, for example, we can see zeta that has a distance given by the function that is 0.7, and hence we free obtain the robustness radius. It's important to note that the robustness radius r is obtained with only one forward of the model, and hence this is pretty fast. Of course, it's a method that can be said online. The last important property of the unitary gradient neural network of the signed distance classifier is the unitary gradient property. In fact, if x is a point of the domain and we call with x star the closest point in the boundary B, that is the closest adversarial example, then the gradient of the function is exactly a vector with the unitary length that points toward the closest adversarial example. This condition turns out to be a necessary condition in the sense that the gradient of the function in each point is always unitary in Euclidean norm. Moreover, if we know the gradient of the function, then the closest adversarial examples can be found by considering x and moving toward the direction given by the gradient of a length provided by the function itself. Those are necessary conditions, but in particular, the first one can be reverted to become a sufficient condition under certain hypotheses. In this work, we proved, for example, that a function f that is smooth on some open set and that satisfies the unitary gradient property, then is a signed distance function from its own decision boundary. So if we consider the set E of all the point x for which the function takes a negative value, then the two functions are exactly the same. This condition is interesting because it allows to create or to craft signed distance functions by considering, for example, neural networks and imposing the unitary gradient property. Unfortunately, this property cannot be satisfied in the whole Euclidean space because there are geometrical reasons behind this, since in this case the function would be just an affine function, a trivial affine function. However, this statement still holds for non-affine functions when the set U is not the whole input space. Hence, by knowing that a function f which satisfies the unitary gradient condition property then is a signed distance function, we focused on feed-forward neural network, searching for an architecture that satisfies the condition. It is easy to prove that the two conditions in the formulas are sufficient conditions which guarantee the unitary gradient property. The first one is known in the literature as it is named gradient norm-preserving property. Basically, it requires that the Jacobian matrices of all the hidden layers has to be orthogonal. The last hypothesis is the unitary pair difference condition, and it requires that the difference of any two output components of the last layer has to be bounded, has to be equal to 1 in norm, in Euclidean norm. Hence, the aim of this work at the end, it was to develop this kind of architecture that satisfies such conditions. In particular, we proposed the unitary gradient neural network that is composed by orthogonal and convolutional linear layers and gradient norm-preserving activation functions. Those two layers are now known in the literature, and the orthogonal one can be obtained by considering the Cayley parameterization, and that is one of the many methods that there exist. And the activation function instead can be obtained by considering a max-min activation function or also an absolute value. The idea of those two layers is that if we calculate the Jacobian, then the matrices are orthogonal. Moreover, another important layer of this model is the pixel and shuffle layer. This layer basically allows to increase the number of channels by reducing the spatial dimension, still by keeping the GNP property. The last layer instead is the unitary pair difference layer that we also tested in the experiments. And this layer is a parameterized layer so that the condition UPD holds. The condition UPD is that the difference of any two rows has Euclidean norm equal to 1. And this layer can be obtained by a parameterization strategy. Basically, we can apply few steps of the LBF-GS optimizer in order to minimize this loss function in the formula. It's important to notice that this layer can be found by just few steps, few iterations of this optimizer. In particular, 3 or 4 steps are sufficient to guarantee the condition, the unitary pair difference condition. So in conclusion, we tested this model with the one Lipschitz models presented in the literature in order to evaluate the accuracy in the classification and the certifiable accuracy. We discovered that for the 32 sites case, the accuracy is comparable. Is not of course the most high, I mean, but however is comparable to the one Lipschitz model. And we noticed that by increasing the input size, the accuracy increases. In another experiment, we compare also the certified accuracy of the models, and the certified accuracy is defined by the ratio of all the corrected classified samples for which the distance from the boundary is larger than a fixed value epsilon. We discovered that for the 256 case, input size case, the UGNN model has and features the highest accuracy. Of course, the accuracy degrades when the epsilon become bigger, since there are less less samples that are so far from the boundary. In the last experiment, we again compare the UGNN model that aims at approximating the sign distance classifier with the one Lipschitz models. Remember that either one Lipschitz model and the unitary gradient model provides a lower bound of the minimal adversarial perturbation. The lower bound can be found with this formula, those formulas. And we try to express this comparison in the figure on the right. The figure represents for each point a sample of the dataset. On the x-axis, we put the lower bound given by the model, and on the y-axis, we consider the ratio between the lower bound and the real minimal adversarial perturbation. Of course, it's not a real one, but it is computed by greedy algorithms. Observe that a perfect and ideal sign distance classifier would be represented by an horizontal line at the height of 1. Just we can see that the UGNN that satisfies the unitary gradient property has this particular form design on the figure, in which almost all the points are close to the horizontal line at the height of 1. The other models features a lower value, and hence they do not approximate or cannot approximate the sign distance classifier. So this is the end of this this seminar, and just remember that in these few minutes we talk about the possibility to achieve an online certifiable robustness, and I just presented 2 ways. One way is to find an online estimation of the minimal adversarial perturbation, and this can be obtained, for example, by solving the minimal root problem that we presented in the beginning. Or also we can change the classification model in order to have a robustness guarantees by design, by construction. So thanks for, I hope it's not late, but I think not. Thanks for the attention. If you have further questions.
So thank you, really thank you again for the great talk. Now it's question time. First we start from the Zoom, and then if there are any, we move to the YouTube. Is there anybody that has questions? Otherwise, I'll break the ice and I'll ask a question myself. So when you were talking about like guarantees of attacks, you mentioned like few attacks, like minimum distance attacks and like maximum confidence attacks. I think I didn't clearly understood what you mean by guarantees. So can you please can you please detail this like a bit more, and then I move to the next question.
Yeah, with guarantees, I meant that those methods, for example, the LBF-GS method or the method proposed by Kalini-Wagner, that is an iterative penalty method, they are known in the in the optimization theories, and they can be supported by theorem, in the sense that the solution has some guarantees of success when under certain hypotheses. Typically, the hypotheses are convexity of the function. Hence, clearly, this does not hold in the deep neural for the deep neural networks. However, close to the to the boundary, we have some kind of convexity with many quotas. However, in some sense, this is one of the advantages of this method that can be supported. I'm not saying that we are sure 100% that the solution can be found. I'm not saying that the solution is global, because it's not true. However, there is this support. It's not, I mean, a mathematical way to say guarantees. It's more related to the safety of using these strategies. However, other strategies are not supported from how to say, an optimization background, so we cannot really say if the solution is the accuratest one.
Oh, okay, because like in this case, when you take like DDN instead of like Carlini-Wagner, you get like a speed up in like other properties, because in Carlini-Wagner you have a free parameter, and then depending on that free parameter, you might, for the loss function that you're optimizing changes, and it's like the minimization of like one distance. So that's why I was confused. Like I couldn't understand which was like the axis we're looking at for like rating the attack. But now it's clear. Thank you.
Thank you.
Are there other questions from the audience?
There is a question on YouTube.
Yeah. I'm removing like both things. So so there is a question from the YouTube chat that I'm forwarding now to you, which is how do we apply the same approximation in a black box scenario, for example, testing ChatGPT?
I would apply, okay, but ChatGPT. Sorry, can you repeat, please, the question?
So the question is, how do we apply the same approximation in a black box scenario? And I think that the question refers to the fact that you don't have access to the gradients of the model, and then which is like the way to estimate this kind of radius when you don't have the gradients.
Okay, particularly interesting question, because I don't know how to think about boundaries and decision boundaries by using ChatGPT, since ChatGPT is not a classifier. However, we can say, for example, that we can use ChatGPT-3 for sensitivity analysis, and then in this case, we will have a function that it provides a statistical measure or a score, that a value that it provides a measure of the, I don't know, happiness of some words or the sadness of some words. In this case, we are again into a classification scenario, and I think the idea is pretty the same. In this case, we will have phrases that are not sad or happy, that are in the decision boundary, and these methods that uses only the gradient can be applied to find, for example, the distance of the phrase or a sentence from the other region.
Okay, thank you. So are there any other questions?
Okay, well, we wait for other questions. Maybe I can ask one. I wanted to ask how does, for the other work, for the classification work, how does it scale? Does it work on big networks, big data set, or is it bounded by some computational complexity?
For sure, there are some issue in the computational complexity. I want to find the proper slide. And so the problem is that we need orthogonal layers to impose the unitary gradient condition, and orthogonal layers can be achieved in different manners. The parameterization strategy is something that is particularly slow during the training phase, but when the parameters are fixed, then we can basically store the weights as a common weight of a network, and hence the how to say, the complexity of the model is exactly the same of another model. A serious, I mean, a problem that we have with this kind of architecture is that the amount of channels cannot decrease only due to the orthogonal layers. In fact, in this case, the amount of channel needs to be the same in order to have this condition here. The only way that we have to increase the number of channels then is to use a pixel and shuffle layer. And so we managed to have this condition. I don't know if it is clear. Another problem, so given this fact, we have that the last hidden state, for example, is an hidden state that is a really low spatial dimension at the end and a lot of number of channels. If we start from a huge image, then the spatial dimension of this last hidden state would be pretty large, and hence the last convolution also is effective and it can work properly. This idea is shown by the table, in which if we use larger images, they are always from CIFAR10 dataset, but if you enlarge the input image, then the accuracy of the model is higher. So I think yes, it can be scalable for larger images. And just the last thing, still in fact for the future works, we have to work to the scalable of the last layer. In particular, we noticed that, for example, with German traffic sign recognition benchmark dataset that has 48 classes, then this model can be particularly tough. It's not easy.
Thank you.
Okay, thank you again. So
yeah.
There is a question from Battista. So
yes, hello Fabio. Nice talk. Thank you.
Hi. Thank you.
I just wanted to ask one thing about the first work you presented. In particular, if you can elaborate a bit more on which kind of assumptions you made on the function f to then certify robustness.
Okay, basically the assumptions are continuous and smoothness assumptions. So f has to be smooth, at least in a region of the boundary. I'm trying to search in some. I think this one can be okay. The function has to be smooth in the neighborhood of the boundary. The gradient has to be defined, but this is the case of almost all the networks. And after that, I think nothing else. However, if the function is smooth but particularly complicated, then the radius, the certification radius, can be particularly small. I think I have a slide on the certification radius. Sorry. Okay. The certification radius, that is the radius for which the inequality holds, it depends on two important measures on the function. That is the norm of the gradient, in particular the infimum of this norm, and the superior norm of the Hessian of the model. Just to give you an idea, if you have an affine classifier, for example, then the gradient will be constant, hence this value is fixed and can be set even to 1 by dividing, for example, the weight by the norm of itself. But the Hessian is 0, hence, in some sense, the certification radius diverges to infinity. And in formula, this means that the inequality holds everywhere. For other networks, instead, when the Hessian is particularly small, then we have the problem that, or particularly large, then we have the problem that this neighborhood here, the tubular neighborhood, is so small that basically is too close to the boundary itself. So we decided to not apply an hypothesis on the function, but of course there is some issue when the function is particularly complicated.
Sorry, and this has to hold where? So if for x sampled within the ball that you're considering, or
where is this infimum? This is in the input domain.
So across all the input domain.
Yeah.
Okay. Okay.
Or at least in some neighborhood of the boundary that can be large enough. For example, for images, the square 0, 1 can be a neighborhood of the boundary.
Yeah. Okay. But in general, this is something you cannot check for the whole classifier, right?
This is for sure is a problem, and that's why we focused on the model instead on the method. Because, for example, a sign distance function would have this value here constant because it's 1 by hypothesis, and also there are particular property of the Hessian that cannot explode in magnitude.
Okay, thank you.
So let's see if there
can ask another one.
Let's go.
I see there are no questions in the chat. Please, people, if you have questions, don't be shy. Yeah, I want to go back to the beginning of the presentation where you said that this applies only to digital adversarial examples. So what happens with certification when you don't have a digital adversarial example, but you, for example, you have different settings? Can you can certification be applied also to physical adversarial examples in some scenarios?
So I think that the digital adversarial example is the worst case possible scenario, because of course we can attack each pixel of the image. Hence, if we manage to find a certification in this case, then for sure the environment have to satisfy the same certification, or at least lower, in the sense that, for example, if we know that the magnitude in terms of amount of pixel that can be perturbed is under certain below for the digital case, then for sure, even in the environment, we have still this bound, even because we cannot inject in a camera, for example, a perturbation that perturb each pixel on the. So in some sense, we can say that the digital one is the worst case. Hence, if we solve the problem in the worst case, we have guarantees also in the real world case. The problem of the real world is that the problem of this approach, I think, is that we can be too picky in criticizing these models. So this is one of the possibilities, since we can say, no, these images are not safe, this model is not safe, because by the modeling point of view, the model is not robust, but maybe the model can be safe under only real-world attacks. So this is one of the problems.
Okay, and another question that might be related always on the assumptions. Is this a certification method applicable, or at least some part of it, to other norms, like other LP norms, an infinity norm, for example?
You are saying for the first, for this one, I mean, for the. So
I mean, actually, both.
Okay, the first one partially yes, but we have somehow some problem on the definition of the minimal adversarial perturbation. In particular, if we use the one norm, the L1 norm, then the I don't know if I have some image, then it's not clear how to define, or I mean, the minimal adversarial perturbation can be not unique. That's one of the problems. I think that for LP norm with P greater than 2, then still we can provide estimation of this in this manner. With P equal to 1, I have to think, but there can be there are issues on the definition of the minimal perturbation, and with P lower than 1, it's difficult to say because they are not properly distanced from the mathematical rigid point of view, and hence I don't know if this inequality can be proved. However, for the other work, this is a problem in the sense that the theorem holds only for the Euclidean norm. In general, this theorem holds for manifolds in high-dimensional space. However, this formula here is translated to the sum of the squares of the differences. So there is no, I don't know how, at least there is no possibility to extend to different metric. However, it could be for sure an interesting thing. And yeah, this is related also to the fact that I was saying before, that is, since the Euclidean space, that is the Rn, is flat under the Riemannian metric, then this implication holds only for trivial functions. That's why we need that the unitary gradient property holds in an open set. And again, there are no, it's not totally clear how to convert this with other metrics or other functional in this side of the equation. I hope it's clear, but this theorem holds for example, is particularly interesting for space that has a negative Riemannian curvature, and this is not the case of the images or sounds that in the data in general.
Thank you, Fabio.
You're welcome.
I have a more speculative question, if I can. So, because we are talking, I mean, in general, in this area, we are still talking about, you know, in a sense, toy problems, if you want, because we are considering perturbation models like L1, L2, L infinity, that actually are not so, it's not something that happens in practical problems, right? Imagine that if you have, I don't know, like a scenario where there is a car, an autonomous driving vehicle, which is trained on certain kind of images, and then, you know, you change the environment conditions, and then you have images that are, you know, different illumination, or the level of rain and fog is higher than what you experience in the training set. So the variations that you experience in practice may not be necessarily adversarial, but they do not follow for sure one of such models, right? There's no L2 perturbation in each pixel. So do you foresee any way in which we can maybe try to model these different kind of perturbations and possibly certifying some of them at least? Like something, you know, where we maybe learn the kind of perturbation from data, and then we
No, it's a good question, of course, and it's pretty difficult to focus on both stuff, you know, on the real world scenarios and digital attacks. However, I think a good way to think about this problem is that I was trying to summarize this fact in this slide, that these adversarial examples are just telling us that the models that we are using are not robust by construction, in the sense that we are training models for which the decision boundaries in general, that of course they are not the real world decision boundaries, but those decision boundaries are really, really closed. Close in this case, it means under the L2 norm, that is not so suitable for large images, for example. However, maybe by having a good robustness result on the digital case, this result needs to be transferred to the real world, because this perturbation here is surely a worst case. Oh, sorry, this here is a worst case with respect to a perturbation in the real world like this one. For example, if we know how to modulate the function so that the decision boundary can get farther and farther, maybe we can obtain something that is more robust. And this robustness has to be translated in the real world in some manner. So I think in just a different point of view, if we want to focus directly on the security and directly on the safety of a system, then of course we need first to check under a real world lens. If we want to think the problem from the modelistic point of view, we can still work on the digital perturbations, since they provide more information on the mathematical model.
So what you're saying is that if we ideally were able to push the boundary farther away from the training points, even in an L2 norm, this can give us some robustness against different kind of perturbations. So overall, you need a larger input margin in a sense.
Yeah, a kind of, in the sense that the Euclidean norm is pretty large on images, and it doesn't fit well for high-dimensional data. But anyway, it's related to the possibility of perturbation of perturbing an image with some attack. Understand that, for example, the change in the light is not is not measurable under this norm. However, there are many perturbations, for example, the Gaussian perturbation, that appear commonly, and that still they exist.
Okay.
So I think we are, so if there are any other last question, otherwise I think we can close here the live stream if there are no last minute questions. Okay, I think that we can close it here. So
I think the audience is had a chance to ask the questions. So again, thank you, Fabio, for this explanation. You're the first who brought here certification, and we're all scary of this topic, but it was quite understandable. So thank you again for the presentation, and thank you
for inviting.
Yeah, of course, and thank you all for joining today, and